So, in the last lecture we were looking at a pipe flow, which is an important prototypical velocity profile that we encounter. Okay. If you recall, we had done the momentum balance for a cylindrical shell in a pipe flow in the last lecture, and we had got a balance equation, and that balance equation was of the following form. Okay. So, just to write it once again. Okay, just to write it once again, rho dux by dt is equal to mu into 1 by r d by dr of r minus dp by dx. Okay, so, that was the balance equation that we had got. This slightly more complicated form of the operator is because we are considering a cylindrical volume. We had got a similar equation for the concentration and the temperature fields, but without this additional term here, okay, without this additional term. This additional term is the pressure gradient, the pressure difference between the two ends of the differential volume divided by the distance. Okay. And when we solved momentum transport problems, we had got an equation of the kind rho partial ux by partial t is equal to mu 1 by r d by dr, okay, without a pressure but with body forces we had got plus Fx, where Fx is the body force density, force per unit volume along the x direction. So, the point I am trying to make here is that the pressure gradient acts exactly the same as a force density. Okay. The negative of the pressure gradient in the x direction is equal to the force density. The negative of the pressure gradient is the excess force that is exerted in the plus x direction. That is analogous to a force density. I could have got the same velocity profile if the pipe had been vertical and I had a body force which was rho times g, okay, the gravitational acceleration. So, the velocity profile that you get from a pressure gradient is the same that you would have got from a body force. The pressure gradient is just equal to the body force density. So, that is primarily the role that pressure gradient plays in momentum transfer. It exerts an additional body force density per unit volume. So, in this case I had solved the equations, got a parabolic velocity profile, if you recall here, a parabolic velocity profile. For that we had calculated the mean velocity, the maximum velocity, the shear stress. The velocity profile itself was parabolic, okay, as shown here. The shear stress turned out to be linear. Okay. The shear stress was 0 at the center. The shear stress is proportional to dp by dx times r by 2. Okay. So, it was 0 at the center and increased linearly towards the wall. Okay. The slope is the same on both sides. And from that we had got the expression for the friction factor as a function of the Reynolds number. Okay. Laminar flow, we saw that it was 16 by Re. Okay. At a Reynolds number of about 2100, there is a transition to turbulence and the laminar flow is no longer observed, and I had explained to you what that transition means in the previous lecture. Okay. Even though the laminar flow is a solution of the momentum equation at all Reynolds numbers, it is not a stable solution. Below a Reynolds number of about 2100, it is stable, so that if you put a small perturbation, the system actually comes back to its original state. Above 2100, if you put a perturbation and if that perturbation is sufficiently large in amplitude, the system does not come back to its original state. Okay. And that is what causes the transition to a turbulent flow. The turbulent flow is not steady. Okay. There are velocity fluctuations at every location in all three directions. In a laminar flow, if I plot the velocity as a function of time, it will be only along the streamwise direction and it will be equal to a constant value. There is no cross stream velocity. Okay. And therefore, in a laminar flow, the flow is steady. The fluid fluctuating velocity is 0, even though there may be molecular fluctuating velocities. It is these molecular fluctuating velocities that give rise to diffusion. In a turbulent flow, on the other hand, there is an average velocity when you average over time, but instantaneously the velocity is fluctuating in time. Okay. It fluctuates in all directions. Okay. In all three directions you get a fluctuating velocity in time. Okay. So, you get a velocity, a fluctuation superposed on the streamwise velocity, and you also get fluctuations perpendicular to the plane of the flow. And this is because you have parcels of fluids called eddies which are in correlated motion, moving along and across the flow. Okay. So, the flow is not steady, and therefore, one cannot write a balance equation where one considers cross stream transport due to momentum diffusion alone, due to the shear stress alone, because there is fluid velocity in that direction as well. And that fluid velocity is what transports momentum across the flow primarily. Okay. The velocity profile, if you plot it, looks flatter at the center and steeper at the walls. Okay. The velocity profile, if you plot it, it looks flatter at the center and steeper close to the walls. At the walls itself, the velocity has to be 0. Okay. All components of the velocity have to be 0. The mean velocity has to be 0, but the velocity fluctuations also have to be 0, because the absolute fluid velocity is 0 at the wall from the no slip condition. So, at the wall itself, the velocity of the turbulent eddies has to decrease to 0. Okay. The velocity fluctuations have to decrease to 0. Okay. What that means is that if I go a small distance away from the wall, the maximum length of the correlated turbulent fluctuation has to be equal to the distance from the wall itself, because you cannot have a correlated fluctuation over a larger distance. The velocity has to decrease to 0 at the wall. Okay. Now, analogous to molecular diffusion, where the diffusion coefficients were equal to the mean free path times the root mean square molecular fluctuating velocities, in a turbulent flow as well, one can make an analogy, an inexact analogy, that the diffusivities are proportional to the mean root mean square of the turbulent fluctuating velocities. Recall, the fluid velocity can be decomposed into a fluid mean velocity and a fluid fluctuating velocity in a turbulent flow. This is not the molecular fluctuating velocity, this is the fluid fluctuating velocity, because the fluid velocity itself fluctuates in time. In that case, one can make a loose analogy that the diffusivities will be a magnitude of the fluctuating velocity times a size of the eddies. Okay. This goes by the name of the mixing length hypothesis. Okay. L in this case is the mixing length, the distance over which the eddies mix the fluid, and V prime is a velocity, a characteristic velocity of the eddies, and therefore, the turbulent diffusivities will scale as V prime times L. Okay. And as I showed you, for typical systems, the fluid fluctuating velocity is much smaller than the molecular fluctuating velocity. Okay. The molecular velocity fluctuations scale as the speed of sound of the order of hundreds of meters per second in gases and about 1000 meters per second in liquids. Okay. The fluid fluctuating velocity, on the other hand, is only of the order of meter a second or less. So, there is a difference of about 2 orders of magnitude. The molecular velocities are 2 orders of magnitude larger than the fluid velocities in practical applications. However, the molecular length scales, the mean free path, is of the order of 10 power minus 7 to 10 power minus 8 meters. So, it is smaller than the system size by over 5 orders of magnitude. Okay. Because of that, the molecular diffusion coefficients are much smaller than the turbulent diffusion coefficients if you define it by the mixing length hypothesis. And therefore, the transport of momentum is primarily by turbulent diffusion across the center of the pipe. This turbulent diffusion process is much faster than the molecular diffusion process. Therefore, the transport rates are much higher, and consequently the friction factor is higher, because when the transport rates are higher, the shear stress is much higher, and the friction factor is much higher than that for a laminar flow, where the transport is due to molecular diffusion. However, as you approach close to the wall, the turbulent fluctuating velocities have to decrease to 0. Okay. And as I discussed in the previous lecture, very close to the wall you have a layer of fluid where the flow is primarily viscous, because the turbulence fluctuations have to all decrease to 0 by the time you come very close to the surface. Okay. The turbulent velocities have to be 0, and therefore very close to the wall the turbulent fluctuations are damped out, and you have a region called the viscous sub layer where the flow is primarily viscous. What is the length scale of this viscous sub layer? It is not the macroscopic size, the pipe diameter r, because the viscous sub layer is actually confined to a thin layer near the wall. What determines the thickness of the viscous sub layer? Okay. The only quantity of relevance here is the shear stress in the viscous sub layer, because the shear stress, as I showed you, is a linear function of distance from the center of the pipe. However, as you approach close to the wall, if this thickness is much smaller than the radius of the pipe, the length scale for the shear stress is the radius. Therefore, if this thickness is much smaller than the radius, then within this region you can consider the shear stress to be approximately a constant, okay, and approximately equal to the shear stress at the wall itself. Okay. So, from that I can actually get a velocity scale, okay, from the shear stress. Okay. I can get a velocity scale from the shear stress. It is called the friction velocity. Okay. It is based upon the wall shear stress. Okay. It is called the friction velocity. I get that from dimensional arguments by equating rho u square to the shear stress, and that gives me the friction velocity as u star, which is equal to root of tau w by rho. So, that is the relevant parameter, the relevant velocity scale within the viscous sublayer. Okay. Now, how does one get a length scale? Okay. We know that within the viscous sublayer, viscous effects are important, and therefore, the only other dimensional parameter that is of importance is the kinematic viscosity. Okay. And from that you can get only one length scale. Okay. L is equal to nu by u star, okay, where u star is the friction velocity. Okay. Therefore, I can scale the distance from the wall by this length scale. Okay. If y is the distance from the wall, I can define a scale distance y plus. It is called the distance in wall units. Okay. This length scale is what is called 1 wall unit, because it is based upon the shear stress at the wall. Okay. It is based upon the shear stress at the wall and the kinematic viscosity. So, it is called 1 wall unit, and y plus is defined as y u star by nu. Okay. So, for the flow very close to the wall, y plus must be the relevant length scale. The total radius of the pipe is not. Okay. Similarly, I can define the velocity ux plus is equal to ux by u star, because that is the only velocity scale very close to the wall. Okay. And close to the wall you would expect this velocity scale by the friction velocity to be a function of this distance from the wall in wall units. Okay. So, that is the fundamental relation close to the wall. Okay. If the system is completely viscous at the wall itself, okay, if the system is completely viscous, there is no cross stream diffusion due to turbulent velocity fluctuations, because they have already got damped out. Okay. And if the flow is purely viscous, then you require that the wall shear stress has got to be equal to the viscosity times dux by dy at the wall, because the flow is purely viscous. Okay. Or I can define it by the density. This is equal to nu dux by dy close to the wall. Okay. And if I express this now in terms of the scaled velocities, okay, if I express this in terms of the scaled velocities, okay, this can be written as nu, okay, u star divided by, okay, nu by u star, okay, d of ux by u star by d of y u star by nu. Okay. Just expressing it in terms of the scaled velocities. Okay. And this is equal to u star square, okay, d ux plus by dy plus. Okay. This is equal to tau w by rho. Okay. Just expressing in terms of the distance expressed in wall units and the velocity scaled by the friction velocity. Okay. The friction velocity is u star. Okay. But we know that u star square is just equal to tau w by rho. Okay. Therefore, very close to the wall, the velocity scaled velocity ux plus by dy plus should be equal to 1. Okay, because I have used the wall shear stress to scale the velocity, therefore, dux plus by dy plus has to be equal to 1, and this implies that very close to the wall, okay, ux plus is just equal to y plus, the distance in wall units, okay, in the viscous sublayer. Okay. Experimental studies show that this law is applicable approximately up to about y plus of about 30. Okay. Y plus less than 10 you see a linear velocity profile. Okay. For y plus less than 10 you will see a linear velocity profile. Okay. Within this viscous sublayer, okay, this linear law applies. The only thing is that I have to define the velocity in terms of the friction velocity rather than the mean flow velocity. Okay. Now, the turbulent flows, of course, when the distance is comparable to the radius of the pipe. In between the two, in experiments it is found that there is what is called a logarithmic layer. Okay. This logarithmic layer can be justified on the basis of matched asymptotic analysis, which I will not have time to go through in this course. Okay. This can be justified on the basis of matched asymptotic analysis, but within the logarithmic layer, okay, this goes as a logarithm of the velocity. Okay. This goes as a log of the velocity. Okay. So, if I express ux plus is equal to a log y plus plus b. Okay. So, there is this logarithmic region where the velocity profile basically goes logarithmically. Okay. And then near the center of the pipe it becomes nearly flat. Okay. This logarithmic layer varies from y plus about 30 to 200 is the classical conventional wisdom. Okay. This is called the von Karman law for the velocity, logarithmic velocity profile in this logarithmic layer. Okay. I should note that this is an area where there is a lot of current research, and these limits, okay, are currently being questioned as to whether they are actually applicable or not based upon experiments in very large systems. However, this law is just a dimensional necessity. A viscous sublayer does exist. Beyond that is a logarithmic layer. Okay. The logarithmic layer can be justified on the basis of matched asymptotic expansions, where these constants are available by fitting experimental data to these logarithmic profiles. Okay. And these constants, there are questions whether they are universal or whether they depend on geometry, whether they tend to the same limit as the pipe diameter goes to becomes larger and larger, whether it is a pipe or a channel, so on. Okay. But conventionally this is approximately between y plus of about 30 and 200 you have a logarithmic layer. Beyond that you have the parabolic velocity profile. Okay. So, that is the structure of the flow near the wall of the pipe. The flow is entirely viscous, very close, logarithmic, and then you have the central region where the transport is primarily due to turbulent diffusion, okay, due to the cross stream mixing due to eddies. And within that region, since it is very well mixed, the velocity is approximately a constant. Similarly, for momentum and mass and heat transfer, the concentration or the temperature will be approximately a constant in that central region. And in that central, therefore, most of the transport takes place across this logarithmic layer and the viscous sublayer close to the wall of the pipe. It is well mixed in the bulk of the flow, where turbulent mixing is the dominant mechanism for momentum transfer. Okay. So, this is a brief summary of turbulent flows. As I said, we are not able to do this analytically because the flow is now 3-dimensional. We have so far looked only at transport in one direction. We have not yet looked at 3-dimensional flows. We have also not looked at unsteady flows. We have focused primarily on steady flows in this case. That does give us what is the laminar velocity profile. It does not give us the turbulent velocity profile, but there are some broad features of the turbulent velocity profile that can be deduced just on simple reasoning. The largest eddies have to be comparable to the size of the pipe. Okay. The velocity fluctuations are comparable. They are smaller, but they are comparable to the mean flow velocity. And it is these turbulent eddies that are primarily responsible for the cross stream transport. As you come close to the wall, the velocity has to be equal to 0 at the wall itself. So, the velocity has to be damped out, the fluctuations have to be damped out by the time you come close to the wall. Very close to the wall, there is a layer over which viscous forces are dominant. Okay. And across this layer, the wall shear stress is approximately a constant. From that wall shear stress, I got only the friction velocity as a dimensional parameter, and based upon that friction velocity, I can define a velocity profile close to the wall. Note that this friction velocity is not the mean velocity. This comes out from the wall shear stress and the density. However, if I define the velocity in terms of the friction velocity and the distance from the wall in terms of wall units, okay, if I define the velocity in terms of friction velocity and the distance from the wall in terms of wall units, then the velocity profile close to the wall is just a linear profile with a slope equal to 1, okay, within this viscous sublayer. As I said, this viscous sublayer, it is valid only when this y plus is much less than about 30 or so. Okay, the limits are variously given as 5, 10 and so on. A conservative limit would be to consider this as just equal to 5, but I said these limits are still under active research. Okay. So, y plus less than about 5 is a good conservative limit when the velocity profile is linear. Okay. Y plus going from about 30 to 200, the velocity profile obeys another law, a logarithmic law. Okay. In this particular case, the distance from the wall is still measured in wall units. Okay. The velocity is expressed in terms of the friction velocity. You get a logarithmic function with constants. These are called the von Karman constants, and depending upon the configuration, these turn out to be universal constants. Okay. In particular, the constant A is approximately about 2.5, okay. This is for a smooth pipe, okay. And then it will change depending upon the roughness of the pipe, these constants could change as well. Okay. So, that is a broad summary of the features of the turbulent flow in a pipe. Okay. So, we looked at steady flows. Laminar flow is steady. Turbulent flow is not steady, but on average it is a steady flow with an average velocity profile which has these features. Okay. So, next we will look at time dependent flows. One can look at two different kinds of situations. One is the unsteady flow, the flow, the time required for the flow to become steady. Okay. So, a typical configuration in that case would be, okay, this is the steady parabolic velocity profile. Okay. However, I could consider a case where initially the fluid is stationary. Okay. So, initially I do not have any pressure difference across the walls of the pipe. Okay. Okay. initially the pressure difference is equal to 0. Okay. So, that initially at t is equal to 0, okay, ux is equal to 0 everywhere, okay, in the pipe. Okay. And then at time t is equal to 0, I apply a pressure gradient. Okay. I apply a pressure difference delta p, okay, across this length at time t is equal to 0. And then I watch how the velocity profile develops into this steady velocity profile, okay, how the velocity increases until it reaches the final steady value, okay, with progression in time. Okay. So, that is the unsteady problem. Okay. The equation for that is of course rho dux by dt is equal to mu minus dp by dx. Okay. The boundary conditions are that at r is equal to 0, I am sorry, at the wall of the pipe, okay, at r is equal to 0, we have the symmetry condition, okay, and the initial condition is that at t is equal to 0, ux is equal to 0 everywhere. How do you solve this problem? Separation of variables. Okay. So, I need to get in this particular case the equation is inhomogeneous. Okay. The equation is inhomogeneous. Okay. Therefore, I need to separate out the velocity into a steady plus a transient velocity. We had already done that for the flow down an inclined plane and looked at what kinds of solutions result. Okay. The exact same procedure has to be used in this case. Okay. Since I have already done it 2 times, I will not go through it in this case again. What you need to do is to express the velocity as a function of a steady plus a transient part. Okay. And the transient part is what I already have, okay, minus r square by 4 mu dp by dx into 1 minus r by r the whole square. That is the steady part. Okay. That is the steady part. Okay. For the transient part, okay, the total equation contains this inhomogeneous term, the steady equation contains the same inhomogeneous term. Therefore, the transient equation will be of the form rho dux transient by dt is equal to mu okay. When I subtract out the steady equation from the total equation, this pressure gradient will also get subtracted out, okay, just as the body force did in that case. Okay. So, this is a homogeneous equation subject to boundary conditions, okay, which are also homogeneous. I am sorry, at r is equal to homogeneous boundary conditions. The inhomogeneity will be at t is equal to 0, ux transient is equal to minus of the ux steady. Okay. At t is equal to 0, the transient part will be equal to the negative of the steady part, because the total velocity has to be equal to 0. Okay. And therefore, you can solve this by separation of variables. The solutions will be in the form of Bessel functions in the radial direction and in the form of exponentials in time, and you can get the constants using the orthogonality relations. Okay. So, this is a simple extension to a pipe flow of the same unsteady problem we had solved for the flow down an inclined plane. Next lecture, I will start another kind of flow, which is an oscillatory flow. Okay. Oscillatory flows are known in the physiological system. For example, flows in the blood vessels are all oscillatory in nature. Okay. How does one get a solution for an oscillatory flow? Okay. So, that is something that I will start in the next lecture. That flow will for us illustrate how a competition between convection and diffusion plays an important role in momentum transport. So, I will start an oscillatory flow in the next lecture. I will see you then.